Hello, everyone. Welcome you all for the third Future Intelligence talk from the FI bi-weekly talk series. From this talk series, we intend to create a platform for outstanding early career researchers to showcase their work and at the same time to create a networking platform for aspiring researchers in the field of AI and robotics to get to know these leaders and collaborate with them at a later stage of their research. So today we have Dr. Thilina Dulantha Lalitharatne, an assistant professor in robotics and mechatronics at the School of Engineering and Material Science in Queen Mary University of London. He has a diverse research background in including human-robot interaction, social robotics, medical robotics, brain-machine interface, soft robotics, and bio-inspired robotics. So today he'll be sharing his experience on multimodal signal sensing and synthesis. After this speech, you will have a few minutes to ask questions and share your thoughts. So, Delina, over to you.
Right. Thanks a lot, Chapa. So can you hear me well? And then can you see my screen?
Yes, everything works.
Right. Okay. Thanks a lot. And first of all, I would like to thank the organizers for inviting me to this inspiring talk series you call Future Intelligence Talk Series, organized by University of Cambridge. Yes, I'm Thilina from Queen Mary University of London. So I represent two centers in my school, Center for Advanced Robotics. We call it ARQ, and then also I'm also a part of another center called Center for Bioengineering. So in this talk, I thought of focusing on multimodal sensing and multimodal signal synthesis, and then specifically toward advancing medical robots. Right. Before I talk about multimodal sensing and multimodal signal synthesis, I would like to start with a bit of a background about human-human interaction and human-robot interaction, because these two main components are a part of the talk that I'm going to give you in this presentation in next few slides. Right. So human-human interaction, as you can see from this figure, I mean, so we humans are actual social creatures. So we interact with each other using different, multimodal, signals. We use facial expression to communicate with each other or interact with each other, and then also we use vocal expressions like just like I'm speaking in this presentation. We use vocal expression, and then also we use haptic feedback, such as we use touch as a sensation, kind of sending messages in between each other. And then also other sensing modalities such as smell, taste, that also quite important in a human interaction. But when it comes to human-robot interaction, we can see similar multimodal interactions as well. So this is, figure on the right is what I see, what I kind of define as a human-robot interactive system. So it consists of two main, main three components: human, robot, and task or environment. As you can see, in between these three components, can be actions, it can be perceptions in between these three components. And then you can, I will go through some of the examples where these these actions are multimodal interactions, and then why we need to consider multimodal sensing and multimodal signal synthesis in these human-robot interaction. Right. To give you a bit more background about multimodal interaction, especially in human-human interaction. So we can basically divide interaction or communication between human and human, or like human with multiple humans, into main two categories: verbal communication or verbal interaction versus non-verbal interactions. within my group, so my group is called Multimodal Human Robot Interaction Group at Queen Mary. So we are interested in non-verbal interaction or non-verbal communication aspects. So this right-hand figure actually shows some of the available non-verbal communication forms or non-verbal interaction methods that human used. Out of all these, I'm specifically interested in facial expression, how we understand human facial expression, and then also how we can use these human inspired facial expression in robots to kind of communicate between human or even between robots. That is one of the areas that I'm going to cover in this presentation. And then also paralanguages, not specifically verbal expressions or vocal languages, but we are interested in paralanguage. So, for example, pain sounds, not necessarily words. So that also another aspect that I'm going to cover in this presentation. And then also I'm interested in haptics or physical sense of touch, physical contact, because that is quite important in interaction. And then finally, I'm also interested in body movements, other gestures, postures, for example, between human and human, and also between human and robot systems. So in this today's presentation, I'll be focusing on three main aspects, as I mentioned: facial expression, and then also vocal expression in terms of paralanguage, and then a bit of haptic and tactile sensing. Right. If I begin with facial expression, as you can see, face is one of the most expressive areas of the human body, and then it can produce quite a lot of number of different facial expression. Of course, you might heard about basic 6 emotions of facial expressions, like pain, anger, happiness, but when it's come to microfacial expression, scientists have found that we can actually express around 20,000 different facial expressions, which is quite amazing. Uh, but one of the key features when it comes to face in humans, because humans are so good at encoding facial expression. Like, let's say if you have some emotions, you can encode these emotions into facial expression in a complex way. But on the other hand, the receiver or the person who are actually receiving this facial expression can easily, in most of the cases, easily understand this facial expression or decode this facial expression in very rapid way and efficient way, because of the highly evolved visual system in humans. So this is a very important aspect of facial expression, because we can use these, fundamental understanding about facial expression and then facial expression synthesis in human face to kind of create similar robotic faces or maybe facial expression with agents with facial expression to kind of communicate between human and or even between other robots. Right. To give you a bit background about facial expression, so facial expression actually, uh, facial expression actually, kind of a facial expression actually generate based on a set of muscles in the face. So we have quite a lot of different muscles in the face, and then these muscles bring together, and then they form a specific unique muscle units or action units. So AUs, in simple term, we call AUs, and then with combination of different AUs, we can actually generate facial expression. And then this particular set of AUs and combined with different AUs and generating facial expression, we call this particular system facial action coding system. Or simply, in simple terms, we call FACS. So whenever you want to make a different facial expression, for example, let's say sadness, a set of muscles actually get together, and then it's kind of kind of come together to synthesize this facial expression. So, for example, in this figure, you can see in order to kind of synthesize sadness, you can, I mean, generally in human, in general, like a typical human, it involves action unit 4, action unit 1, and action unit 15. comes together and actuate to kind of make this facial expression. I mean, if I give a bit more about this facial expression generation, so these are some of the like examples, different facial expression, amusement, anger, like contempt, disgust. But let's say, for example, happiness. So this is happiness facial expression, like a typical happiness facial expression. And then if you think of these to kind of synthesize these in humans, it involves 5 different action units. Action unit 6, 7, 12, and 25 and 26 come together, and they work together to kind of generate this facial expression. So this is very, very, very important, because if you want to synthesize uh, artificial facial expression synthesis, robots in virtual agents. So we need to consider these action units, because we want to replicate as this AAU as close as possible to generate these ultra-realistic facial expressions. So yeah, so that is a basic. These are some basic background about facial expressions. But then, do we have facial expression synthesis systems in robots? Yes, of course we have. So this is something we did. I mean, one of the review papers we published some time back, I think if I remember, in 2021. So we actually explored different facial expression synthesis systems in robot. So you can see this from this figure. So if you go through these from left to right, you can see that leftmost faces are kind of quite abstract. They just consist of like maybe eyes. There's no nose, mouth. So these are very basic, kind of faces, not really high realistic. But it involves low degrees of freedom, or small number of degrees of freedom. But on the other hand, if you go from left to right, you can see that, for example, like the robots like Sophia. I mean, so these are really ultra realistic facial, expressive systems. But then on the other hand, it involves a large number of degrees of freedom, just like human face. So yes, researchers and then developers have attempted to synthesize facial expression in robots. So these are some of the existing, developments in the field. So why we were interested in facial expression specifically in my group, because one of the use case actually I wanted to highlight here, uh, to kind of why we need facial expression, especially in medical domain, because some of the key medical procedures involve facial expression. So one of the key medical procedures usually done by general practitioners is we call physical examination. So physical examination actually involves examining a patient through physical means. So it consists of different sub examination methods, such as inspection, palpation, percussion, and then also listening to sounds of the human body. But in this particular use case, we was so interested in palpation. So palpation is very simple procedure where, as you can see from this video, doctor palpate a human patient, and then the doctor actually look for different cues. One of the main cues is actually facial expression. On the other hand, there are other cues like vocal expression, because patient tend to make pain sounds, which is auditory expression or vocal expression. And then also doctor can kind of feel the patient's body through tactile feedback, so which is another type of feedback. We call it haptic feedback. So physical examination involves multiple feedback. So in this particular use case, we were so interested in vocal expressions. And then the specific use case I'm going to explain in this particular example is remote physical examination. Why? Because we found that there are a lot of issues in physical examination appointment, especially in UK, because of issues like the challenges in NHS, in ability to like access physical examination, like for example during COVID. shortage of physician, and then also like other armed conflicts like all around the world. So we actually proposed a method called face-mediated human-robot interactions system for these physical examinations. So the basic idea we had in our proposed method. So we have main four systems. We have a physician. We had a physician to represent the actual doctor, and then we had a simulator to kind of simulate the patient from a remote end, or like from the doctor's end. We call robotic patient, and then we had a robotic doctor to actually work on behalf of the physician, and then we had a human patient. So the basic idea of this particular study was to kind of understand, can a physician remotely diagnose a patient using a remote medical examination system, and then whether the physician can understand the patient's facial expression from remote end versus another feedback to kind of, to understand these patients' different, pathological conditions. So this was the main study. So to develop the robotic patient, we actually used a face called Morpheus. We developed during our previous studies. So this is actually a video of the Morpheus. So this is actually a hybrid mobile robotic face. So this is actual physical face where we can change the size and shape of the face using a set of motors. I will show a couple of figures later on, kind of videos later on about that. But then high-level features such as facial expression, actually we synthesize using a projector. So we project the high-level features such as complexion, facial expression, using a projector onto the hardware face to kind of synthesize these facial expressions. We use a data-driven technique to design our face. For more face, the design process was like this. So we actually use a database called Chicago Face Database, which consists of around 900 images, 300 images actually, with different intensities, like white, Asian, black, and then different gender, different sex. So we use principal component analysis to understand the most important facial features actually in the human face. And then based on that, we design a hardware face to kind of represent like around 80% of the facial features that represent a particular ethnic or gender background to kind of represent using the hardware face. And then we use equivalent virtual face to kind of project the facial expressions. And then this is the physical system, the face that we developed. So it consists of basically also motors where it can kind of it can change those motors can be used to kind of change the morphology of the face, like this in this video, the right-hand video. And then we use this face to kind of develop a remote patient doctor system, where the main study was to kind of to understand whether we can use facial expression during these remote medical examination systems. So we focused on only the visual feedback in this particular study, because we know, as I already mentioned, physical examination a multimodal system where you have auditory systems, auditory feedback such as pain sounds, and then also like haptic feedback such as feeling of touch. So we didn't really consider in this particular study those feedback, but we only focused on visual feedback. And then we had two different visual feedback in this particular study. So we had facial expression feedback, and also we compare that facial expression against another visual feedback, like a color map. So the idea was that so in one end, doctor palpate, or like a participant palpate the robotic patient. So this is just imagine this is abdomen of the virtual patient, and then robot actually follows that movements, and then this end actually represent the actual patient, and then the main objective of the experiment was to find an embedded nodule, so representing like a tumor condition, to find that nodule using facial expression versus another feedback, in this case, a color map. So yeah, and to give you a bit idea about this clearly, so I can show you video. Yeah, you can see a participant palpate on a robotic patient this end, and then the robot actually follows this motion. And then try to find this, there's a nodule over here, I don't know whether you can see it. There's a tiny hard nodule we embedded on this silicon phantom. And then we ask the participant to look at the facial expression and then try to identify this nodule location based on the facial expression. And then we kind of compare this against another feedback. You can see from this video where we use another feedback, like a color feedback, a tactile feedback, instead of facial expression to kind of detect this nodule. So the main idea we had in this particular study, we had a tactile sensor array here, and then we translate this tactile sensor data into in one study into a facial expression. We map the tactile sensing data into facial expression. The other study, we map the tactile sensing data into tactile color map, and then we just want to compare how humans are good at identifying facial expression in this kind of medical robotic applications. And then we found that face-mediated human-robot interaction, which is like using face, leads to statistically significant improvement in localizing the hard nodule. And then without compromising nodule position estimation time. So it was quick as using color map. And then we kind of highlighted that the inherent power of facial expression as a communicative signals in this kind of application, this kind of robotics application. Right, so that's one study that I wanted to highlight since I don't have a lot of time, so I will quickly go to the next study. So in this use case, we actually tried to model the auditory pain signals, because so far we discussed about vocal expressions, vocal expression synthesis, but in this particular study, we tried to replicate auditory pain expressions because, as I said, this is also involved in the physical examination, because we want to develop a robotic simulator to train medical students in palpation training. But then palpation, as I mentioned before, or physical examination is a multimodal examination methods where we need to synthesize vocal expressions, as in this study, and then also facial expression, as I mentioned in the previous study. So in this particular study, we tried to synthesize vocal expressions. So you can see from this video, probably you might be able to hear it as well. Yeah, when participant palpate, you can hear the sound. Yeah, I can try to turn sound. Yeah, so this study was very primarily because at the moment, I mean, when we are doing this study, there were no models actually model the relationship between the palpation and the vocal expression. Of course, we knew that there should be a relationship, but we couldn't find any background study about this particular area. So we actually assume that the pain expressions are actually behave like a Gaussian pattern, where with the higher intensity of pain, we try to synthesize a bit higher pitch volume sound to represent that, and then we try to map the palpation force with this pain sound. So that was the initial study actually we did, and then in one of the recent work we actually extended that to kind of actually model the relationship between haptic and the haptic the haptic and the auditory feedback between. So in this particular study, we try to model the pain expression during abdominal palpation. It's actually ongoing study. So the basic idea here is that participant palpate, and then the system generate a pain sound, and then the participant can kind of rate that pain sound is appropriate or not, and then based on that, we actually trying to build a map to kind of represent a relationship between haptic or the palpation force and the pain sound. So this is an ongoing study. Right, and then yeah, I'll quickly go through last two slides, and then the last study, the last use case I want to highlight is that about the tactile feedback, because so far we discussed about auditory pain expressions, and then we discuss about you know vocal expressions. Sorry, we discuss about vocal expression, and then we discuss about uh, visual expressions or the facial expression. But then there's one missing key element was that haptic feedback, because as I said, palpation involves these three main feedback systems, feedback signals actually, haptic, vocal, and then facial. So in this particular preliminary study, Saitran, one of my master students, actually, he's trying to build a wearable tactile sensing glove to be used in remote physical examination. So the idea is very simple. So these tactile gloves consist of two tactile sensors actually using we developed using pneumatic pressure sensors, and then with the use of silicon air pockets, and then it can be used to kind of detect the stiffness of the material, for example, being palpated. So this is like a very simple idea. So when you palpate, you can kind of detect the tactile force and then the indentation. And then we further extended this into to detect the palpation location as well. So the generic idea we have is that so whenever person use this tactile sensing glove, they can actually go through their body to kind of detect any abnormalities using this platform. Because it can be used to detect the stiffness, like any stiffness variations of the soft tissues in the body. So yeah, so that's the latest from my group. Yeah, I mean that's I think that I was planning to kind of discuss in this presentation, and then thanks a lot.
Thank you very much, Thilina.
Yeah.
It's very impressive that facial expressions can be an interesting tool, not only for social interaction, but also for diagnosis and many other useful tasks. I have a question about
Mm-hmm.
multimodal sensing. Since you were talking about multimodal signal synthesis, how multimodal we can go given the boundaries we have? Let's say we have hardware limitations, and as well as we don't have many existing models to decode nonverbal messages, for example. So how can we deal with these limitations and still we want to do the multimodal signal sensing?
Yeah, I mean, that's a good question, kind of hard question, I think. Uh, yeah, one of the things I can kind of discuss is that, like, when it comes to multimodal sensing, as you said, there are a lot of different multimodal, multimodal modalities actually in interaction. I mean, five basics, sensing, and then also feedback methods are like, visual, auditory, haptic or tactile, and the smell and taste. I mean, these are five, but there are like other sensing mechanisms, like even like, for example, biosignals that also like EMG or electromyography or brain signals. I mean, these are uh, another set of multimodal feedback. So we can actually use these different feedback to kind of improve robots, not necessarily just the medical robots. But I think to answer your question, how we can kind of decode, for example, especially non-verbal, signals, like facial expression, vocal expression. I think uh, first thing we need to understand the fundamental behind how these signals generate. I mean, signal generation in these signals in human body, because otherwise, like we can't understand anything because we cannot really synthesize without these models. So I think that's the first element of this, and then maybe try to find kind of we had to do, like, obviously even though we maybe like it not, so we had to do like bit of behavior studies to kind of understand how human actually use these signals to kind of communicate to each other. So for that, I think multidisciplinary group approach, I think, would be really important, because I'm a robotics, but then I'm from the engineering background, but then I mean, we need to collaborate with different expertise from different background. So for example, psychophysics, psychology, from the medical background, even the neuroscience. So I think that is quite important aspect in my opinion, because I think we need to have a bigger group to kind of understand and decode these different signals. And then probably if we understand them correctly, probably we can kind of, use that, I mean, these understandings or this knowledge to kind of synthesize artificial multiple feedback. So that is my kind of opinion.
Okay. Well said. Thank you very much, Thilina. Thank you
Yeah.
very much for joining us today.
Yeah.
And I have a few announcements before I conclude this session. Um, so we are a team of researchers from University of Cambridge hosting this talk series to bring forward exciting research from early career researchers. We usually invite one speaker to share their research, share his or her research, and also provide networking opportunities for the audience to ask questions and contact these speakers later on to see how they can collaborate and get on later. But our next session will be special, and we will be inviting Galnush Shakarami from Max Planck Institute and Keik Shue from National Nanjing University. And we have two speakers, so we thought of hosting a panel discussion after this talk session, which is scheduled for 13th of August this year. And the time will be 11 UK time, that means UTC +1, to accommodate both the speakers and as many participants from the audience worldwide. So that's it for today. Thank you very much.